Well, first thing I'd like to do is introduce everybody to the new class website. The old one you should be familiar with if you've used it at all. It had some resources up there. Let me look at the published version, make sure I'm looking at the site that you guys could see. Okay. Under the physics tab is all the stuff for you guys. So it had one-dimensional motion, two-dimensional motion, forces, work and energy, waves, and sound is what we're working on right now. Now again, this is the old website, so as you can see there's not very much on there for this unit. But if we head over to our new website, which I have linked at least once in our Google Classroom, you will see this is our starting page. So just kind of a quick overview of what's on here. There's fact of the day. I've been taking this from my fact of the day science calendar and just updating this daily. Just some interesting stuff. The freshmen are using this more than you guys will be. That was weird. If you miss seeing what the heck I'm up to, you can look on this, what's Miss M making right now? Well, it's got all the different things that I'm working on. Just to, reach out. If you guys want to tell me what you're working on, I would enjoy that. I think it's fun to know what everybody's doing for fun and not just for work. Now, something that you guys will actually get a lot of use out of is the Symbology Guide tab. So the Symbology Guide, I made up this nice table so that way you can see all the different variable and unit meanings. So if you forget what a letter means or what it's symbolizing, you can look back on this table. It has all the capital letters, lowercase letters, and the Greek letters as well. Now you can see not all of these letters are used. I try to update this as we go. Everything should be in there. If you see anything missing, let me know, but most of these things should be in here. Even those letters that represent a specific value, such as speed of light is 3 times 10 to the 8th meters per second, is lowercase c. We can see that value is in there as well. So that is something very useful for you guys. Right now, if we go under the physics tab, we are in the unit of light. This is me trying to be punny again, some light reading. This is from my, what's that book called? I have it right here, Physics Without the Boring Bits. I took some scans of some of the more interesting ones if you guys want to read those. Not only are they interesting reads, but they also have some good information in them. So it has a little bit about stealth technology, which you might not think is useful, but it tells you about how light actually behaves in different situations and why it can be rebounded in different things. This one says how to harness starlight. As you can see, it talks about matter waves, star power, solar thermal energy, and cells, which are really interesting as we're talking about waves. Now again, those are optional readings, but I just want to show you where those were. We just started our light unit last week, and really we're just getting into Snell's law. This is what we're going to be focusing more on today. I had provided a list of some of the common N numbers for common materials. We'll go over what the N number is again here in a few moments. But as far as finding a reference page, please use this one. If you try to find a reference page on the internet, there are hundreds of websites that will give you quite a variety. These are the common ones that you'll recognize, and the ones that I will be using. So there is no need to go off into the deep end of the internet to try to find these numbers. They are right here on the website. I will be posting videos of me working out problems and stuff like this where we do a live lesson on this page as well. This will be continuously updated as we go into different parts of light. Okay, right now where there's only Snell's law because that's the only thing we've covered so far. I've also added some other YouTube links that I think you might find helpful. Personally, I think they're kind of dry, but they're good information, and if you don't enjoy me trying to talk about it, or if you still didn't understand it from me, it's at least a secondary resource, okay? If we look into your Google Classroom right now, you can see this whole live class thing that nobody showed up for, and I'm very, very sad. But announcements like that will be there. I'm planning on doing a live class at least once, if not twice a week from here on out. We can have a discussion in that post there if you want to add like a class comment in there. Okay, and say what time or date would be best for you. That would be ideal. So that way we can all talk together and have live questions. I know a lot of you have been struggling with some of the stuff from not last week because that was spring break, but the week before. Okay? Having a live class discussion about it is the best way to get your questions answered because I can draw on things, I can show you things, I can show you, point out links, we can have a live discussion about it, all those things, okay? But if you don't show up for the meeting, everything gets harder. Alright, and now again, it's not required, but it'll make your life a lot easier. Now, since there's no questions, because I'm the only one here, we're going to head right into our thing here. Okay, so we're going to talk about Snell's law, how to use Snell's law. Last week, week before, the last week we were actually in session, we started talking about what Snell's law is. If you recall, let me bring up that table again so you can see it. It's the old website, go ahead and close that. Okay, if you recall, these N numbers refer to the hardness of a substance, or how hard it is for light to go through. So something like air, we see it has a fairly low N number. You cannot have an N number that is less than 1. 1 is the absolute minimum. That is a vacuum. So air having an N number of 1.00293 means it is still very, very easy for light to go through, but there's still at least some minute resistance. If we look on this table here, we can see that, let's see, looks like silicon has one of the largest N numbers, which means it is one of the hardest things for light to get through. Now, the highest number I can recall was around 7, and that was for a totally opaque substance. So there's not really a huge range. It's usually between 1 and 7 for these N numbers, but they have a huge influence, and that's what we're going to look at today. Now, if we look back at our example here, we can see it says, example 1, a light ray is traveling at a 15-degree angle in air. Find the change in its angle as it goes into water. So what we're going to do is, of course, write our knowns first. I'll go ahead and do air in red. So let's see. We know that the light ray starts off traveling at a 15-degree angle in air. So I'm going to put my angle for air is 15 degrees. The other thing I know about air is its N number. Unless I'm telling you to find the N number of something, you should assume that you can find it in a chart. Okay, so we're going to look at air, which is 1.00293. I'm going to put that on my table here. 1.00293. Says find the change in its angle as it goes into water. Now, if it says just water, we're going to assume it's a liquid. Unless it says water vapor or ice, we're just going to always assume that that means liquid. So for water, N of water, we'll look that up on our table. I believe it's 1.33. Nope, forgot a 3. 1.333. And this is all we know. Snell's law, if you recall, is N1 sine of theta 1 is equal to N2 sine of theta 2. This is the relationship as the light travels from one medium to another. In this case, N1 is going to be in air. This is all the description that we need. We don't care about the frequency, we don't care about the wavelength, we don't care about the amplitude. None of those things actually have any effect on how the light is going to bend through these different substances, which is part of the interesting thing. In fact, the only thing that's actually would affect this besides these two factors would be speed. But since it's light, the speed of all these things is always going to be 3 times 10 to the 8th meters per second. That's the speed of light, and we never really have to factor it in because it doesn't change. So our 1s are going to be in air, and our 2s will be in water. Okay, notice I have a protractor off to the side here. I'm going to be using that. Unfortunately, since we are online learning now, we won't be able to graph this, and I won't be able to show you real life examples of how this works as well, which is, yeah, it's just really unfortunate. So I'm going to show you how this actually looks graphically, but you're only going to be able to solve mathematically. I don't expect you all to have protractors and graph paper and be able to do all this accurately enough to be able to do it. It's going to really make life hard when we get to further things like lenses, but for now, just know I'm going to be doing the graph so you can at least see it. Let's solve mathematically first though. Now we have theta of the air, the n number of the air, and the n number of the water. Therefore, we must be solving for theta 2 here. That's our only variable left. We need to rearrange this equation then to solve for theta 2. We're going to leave this side alone on the left here. And I'll go ahead, let's do this in, we'll do this in black. So I'm going to take n1 sine theta 1. I'm going to divide that n2 to the other side. Okay, and that leaves us with a sine theta 2 on the right side. I'm going to go ahead and switch these just to be consistent. So I have sine of theta 2 is equal to n1 sine theta 1 over n2. And then we take the inverse sine of this to get it to the other side and get theta 2 by itself. So theta 2 is equal to the inverse sine, and remember, just like with multiplying and dividing, you need to take the entire side, okay? You're not just taking the inverse sine of one piece of this, you're taking of the entire thing. So it's the inverse side of inverse sine of n1 over n2 times the sine of theta 1. That's how we get theta 2 alone. Now we can plug in and solve. Theta 2 is equal to the inverse sine of n1, which is 1.000293, divided by 1.333 times the sine of 15 degrees. If you're using a graphing calculator or a scientific calculator at home and not some sort of online application, please make sure that it is doing the sign of the angle in degrees and not radians. Otherwise, that will completely screw up your answer. If we plug this in, I'll do it piece by piece. 1.000293 divided by 1.333 is 0.75. So sine to the negative 1 times 0.75 sine of 15 degrees. Okay, let's see, 0.75 times the sine of 15 degrees is 0.194. Oops, and we're going to take the inverse sine of that, so I need to rewrite that a little bit differently. The inverse sine of 0.194, and I'm just carrying everything along rather than retyping it in my calculator, so there may be some rounding error if you're trying this at home, but it should be approximately equal, and you get 11.19. Now what's the units of this? It's the same as the units over here. We haven't changed anything. This is going to be in degrees. Speaking of units, you may notice that these n numbers do not have units of any kind. That is purposeful. I didn't just forget them, though I wouldn't blame you if you thought I had. The n numbers here do not have units. They are experimentally found, and they are just a ratio of how dense a... Well, no, I was almost going to say solid. It's just a ratio of how a substance, how dense a substance is, how dense the molecules are in their arrangement. So these are numbers that are actually experimentally found over thousands of trials by scientists. There was no other way to find these numbers. They are not mathematically found. They are only experimentally discovered. Okay? Now, we have part of our answer here, but it says find the change in its angle as it goes into the water. Therefore, we need to subtract since we are finding the change. 15 degrees minus 11.19 degrees gives us our change in angle, and that is a change of 3.81 degrees. Now, you may be looking at this and say, alright, cool, math, no idea what it means, but I can do that. Well, that's kind of not the point. So we want to make sure that we understand what's actually going on here. Let me move my protractor out of the way here. Move that down there for just a second. I'm going to show you what this looks like graphically. We're going to take our two mediums here, separated by a line, do air in red and water in blue. And we use what's called the normal line down the middle here. It doesn't have to be necessarily in the middle, it's just a good starting point if you only have two substances. Okay? Now, these angles over here are measured from that normal line. They are not measured based off the x-axis as you might expect in math. I'm going to use my protractor so I can do my angles more accurately. If I ever have you do this on paper, which I haven't decided if I'm going to torture you with that or not yet, I won't expect it to be accurate like this. Okay? So do our air, which was at 15 degrees. So 90 subtract 15 puts us at 75. Move this back out of the way. Go back to our red. And again, this is 15 degrees from the normal. So I'm going to connect down to that starting point, and a light ray is traveling down. This is our 15 degree angle that we measured with the protractor. This is the light ray as it starts out. This is our starting light ray. As it transitions from air to water, which you may have noticed this in real life if you've ever been to the beach or a lake or anything, you might notice as you get in the water, maybe your legs look a bit shorter. That's because the light actually starts to bend because of the density of the water compared to the air. And we proved down here that it changes to an 11.19 degree angle compared to the 15 degree. If this had been a different starting angle, that different ending angle would have also been different. However, in this case, it's just this. So I'm going to bring this up here, erase this, rotate my protractor around, line it up with the green line, use blue. Again, this is 11.19, so we're going to subtract 10. Put it at about 11 degrees. And then connect our lines. Okay. Now, nobody's here to ask any questions, but that is the end of that example for today. Today and tomorrow, I'm just going to ask that you guys try a couple of problems like this, and starting either Wednesday or Thursday, well, it won't be Wednesday, either Thursday or Friday. We'll see how you all do with that first. If we want to do another live session on just that, we'll start talking about example 2 here, which tells us to graph a light beam going from air to water vapor, to water, to ice, and then back to air. So going through several different mediums and then back to the original. That's a completely different scenario. This is actually a fairly complex example, so we are not going to tackle that today. We will tackle that either later this week or next week. As always, if you have questions, please feel free to email me. I live answer things at least between 1 and 4. I'm usually on earlier than that and later than that. But again, please, 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 put down here what times and days are best for you. I would very much like us, if not all of us, to be there, most of us to be there so we can have live discussions and tackle the problems, because it's never just one person that has a question. All right. See you soon, hopefully.